information. So today we'll discuss variational. Okay, this is one of the approximate methods used in quantum mechanics. So what is the thing is that you have the Hamiltonian, and let's say H psi is equal to E psi, cannot be exactly solved. Okay. Then suppose if we can write, that is, if we can write this Hamiltonian as H0 plus some H prime, where the energy content of H prime is much less than energy content of H0. Okay. And so if we can write like this, and if H0, I can write this as psi 0 is equal to E0 psi 0 can be exactly solved. Then we can use what is called perturbation theory. In this case, I'm assuming that this Hamiltonian is independent of time, so it's a time-independent perturbation theory. What is that to get?
Sir?
Yeah.
Sir, here I have always a doubt. When you write H prime mod is less than H0 mod, and do you mean norm of H prime or what? Norm of the operator or what?
No, that is why I said, I think I didn't write, but I said energy content. That means classically this is an energy.
Yes,
so that energy corresponding to H prime should be much smaller than H naught.
But it is an operator, no sir? How energy?
No, even before you think of it as an operator, okay. So there is some. It has some energy scale, right, corresponding to every term.
Yes, sir. Yes, sir.
So that energy scale has to be compared. That is why I said this word is very important. Energy content. So I am choosing to use this word because it is that quantity of energy represented by that term.
Yes, sir.
Is what you have to compare.
Okay. That means if I solve H prime somehow, then the energy levels of H prime, the order of magnitude that you are.
No, energy levels is different. See, for example, if let's say you have hydrogen atom, okay,
Yes,
and then you apply magnetic field.
Yes, sir.
In magnetic field, let's say in B field. Now what happens is that you have H, which is given by H0 plus, then you have a H prime. Now your suppose assume that this B field is weak. Okay, then what happens? This H0, which is corresponding to the kinetic energy plus E square by 4 pi epsilon naught r. This is the hydrogen atom kinetic energy plus potential energy. Plus, you may have what is called E by 2m, 2 E by twice mu times you have angular momentum plus let's say 2 times spin dot b.
That spin coupling term, sir.
Correct. So this is how the magnetic moment of the electron coming from the orbital motion of the electron and spin of the electron will couple to the magnetic field. Now this will be your H prime. Okay. So if
Yes,
V
sir.
is weak, now this energy, that is the interaction energy of the magnetic moment with the magnetic field, this energy will be smaller compared to this energy.
Yes, sir.
Now only if this energy is smaller,
Yes,
now
sir.
you can say that this will actually whatever energy levels corresponding to this particular Hamiltonian will be
Yes, sir.
modified.
Yes, sir.
Suppose if you apply this field to be very high, then what happens? Maybe this electron and proton are now torn apart,
Yes, sir.
okay, and they are no longer a hydrogen atom, and
Yes, sir.
maybe electron and positron independently will make some kind of a cyclotron motion.
Yes, sir. Oh,
Okay, so that will be a different problem. So these energy levels will no longer be valid for that. Now you have to solve that problem, and then this electron proton interaction may be like a perturbation to that one. So it is in that sense we must consider the energy content of these terms.
sir, that means the new energy level and the unperturbed energy level, their difference is much smaller. That yours.
Yes, yes, because only then the perturbation works.
Yes, sir.
So perturbation will simply say that it will modify it, but the modification is not very large.
Yes. Oh, okay, sir.
Yeah, so that is what this perturbation tells us.
Energy content. Okay, sir.
Yeah, energy.
Thank you, sir.
So that is what about time-dependent perturbation theory, time-independent perturbation theory. Now, in the last class, we have seen that in cases where the potential varies, so if you have, so you, first thing is that our Hamiltonian, we are not able to visualize as some large part which can be exactly solved, like H0, which is not always possible. But if you can say that this V, the potential is slowly varying, okay, slowly varying, then you can use what is called the WKB that we have seen last class. So if you are not able to write it as H0 plus H prime, and if you have a special situation where this is slowly varying, then you can use WKB. Now, if you cannot write like this also, and potential is also not slowly varying, then you have to use variational. So H is something which you cannot write it as H0 plus H prime. That means there is no part of it which can be exactly solved. And potential is also not slowly varying, in which case you use variational technique. So variational technique is so variational method is in that sense a little more general, but you can only use it for determining the ground state. Okay. So as we have seen in the last class, the WKB approximation sometimes will give us all the energy eigenvalues, of course approximate energy eigenvalues. And perturbation, you can calculate perturbation correction to any energy level. Variational method will give us the ground state, but that's also very important because when you have complicated systems like molecules or crystals like that, which are many atoms are there, many electrons are there, then their ground state is what is important, and ground state is what is important because that is what corresponds to equilibrium of the situation, and deviations from the ground state will tell us how actually this molecule or system will react in terms of making chemical bonds and things like that. So most of quantum chemistry uses this variational method. Okay, so um, variational method is essentially the following. So you are interested in finding the ground state energy. Okay, so let us say that I have Hamiltonian H, let H be the Hamiltonian, and and let E uh, 0 be ground state energy. Ground state energy. Of course, which we do not know. We do not know, but there exists a ground state, and that has got certain energy, E0. That is what I am calling it as E0. Okay, so please follow this argument carefully. This is the formal argument, and after that, whatever we are going to do is an application of this formal argument. Now, um, for any state psi, this is not necessarily an eigenstate of H. This is not necessarily the ground state. Okay, so not necessarily ground state. Not necessarily the even an eigenstate of H. So for any state psi, let's put these things in the bracket. For any state psi, define Eg. Okay, define Eg as the expectation value of psi H psi. Okay, so if you are using a Dirac notation, this is written as psi H psi. I'm going to define expectation value of this. This is any given state, you can find out the expectation value if you know Hamiltonian. This is something that you can calculate.
Sir?
Yeah.
Sir? So that should be less than equal to the upper bound is expectation value.
Yeah, so I am going to define Eg as this one. Okay. And then then your E0 has to be less than or equal to E. Okay. See, this E0 is the ground state that I have denoted here. E0 be the ground state energy, which we do not know. But what I am saying is that if you can calculate this expectation value and then call that as Eg, this serves as an upper bound for the ground state energy. Or in other words, your ground state energy is smaller than or equal to this Eg. Okay, so this is basically your variational principle. Now, proving this one is very easy. So let us write down the proof. Okay. So let us say let h phi n is equal to En phi n. Okay. So here this set of phi n are eigenstates of H. Of course, we don't know them. If we know them, then we don't have to bother. They are unknown. But whose existence is guaranteed? What guarantees this existence? Because H is a Hermitian operator, the eigenstates of every Hermitian operator exists. Not only that, they will form a complete orthonormal states. Correct? That is what we have studied in our earlier postulates. So they not only exist, but this also whose existence is guaranteed and form a complete orthonormal basis. Hmm? What is that? This one and Hello, am I audible?
Yes, sir.
Yes,
Yes,
sir.
sir.
Yeah, so there was some problem with electrical connection. Yeah, no. So suddenly there was some spark at the plug. Okay, so you are able to see this, right? Whatever.
Yes, sir. Sir, I have a question.
Yeah.
So you told that variational methods are useful for molecular interactions. It's a very useful in quantum chemistry. So
Yeah.
a few days back, I read a paper about MESP, molecular electrostatic potential. So is there the perturbation term Hamiltonian is MESP, sir? Molecular electrostatic potential. Or
Yeah.
should we use it
So
in variational methods?
no, usually perturbation doesn't work there. You have to use only variational methods. See, for example, all that we do in terms of Hartree Fock method,
Yes, sir. Still
density functional
consistency.
theory, all these things are based on variational methods.
Yes, sir. Sir, actually, I was reading, is there hydrogen bond radius, a paper called Is there hydrogen bond radius? They are saying that the hydrogen bond radius is the minima of the field in molecular electrostatic potential. So
Yeah, yeah.
from the nucleus of the hydrogen to the minima of the MESP, that is the hydrogen bond radius. So should that be considered a perturbation term, sir?
No, it's not perturbation. I think it is only variational method. You will understand that when we discuss this one.
Okay,
So
sir.
let it just
Okay.
so whose existence is guaranteed and forms a complete orthonormal orthonormal basis of state space. Okay. So if this is guaranteed, then you can always say that so mm, any arbitrary state I can be written can be written as psi is equal to sum over n from Cn into phi n because it forms a complete orthonormal basis where Cn is equal to the inner product of phi n with psi. Okay. Now that it is also complete and orthonormal, you can get so we get you can normalize this one. That is uh, psi is equal to 1 implies sum over n modulus n square is equal to 1. Okay, so we can write like this. So whatever psi that we have taken here, okay, so we have taken this now. for any state psi. Now this state psi can be expressed as a linear combination of this complete set of states phi n. So far everything is formal. I don't know these phi n's, but still I know that they exist, and if they exist, they can be written like this. Okay. So now suppose if I am asking what is Eg, so Eg is equal to expectation value of psi. So I think it is a little bit bad that I am switching back and forth between this Dirac and non-Dirac notation, but I am sure you are able to understand. So this is nothing but sum over some m Em star phi m into H into, now I will have sum over n Cn phi n. Why I am writing m and n? Because these are two functions. So this psi can be written as this quantity, and this bra psi can be written as. Now this can be written as sum over m comma n Cm star Cn phi m H phi n. But what is phi m's and phi n's? These are eigenstates of H. So what is H acting on phi n? H acting on phi n is En phi n. Correct? So that gives you sum over m comma n Cm star and Cn, and I will have En energy eigenvalue into phi m, inner product of phi m and phi n. But they are orthogonal, so this is a chronicle delta mn. So sum over m comma n Cm star Cn En delta m. So we have a double summation over m and n, but if you just look at sum over m, except m equal to n term, all other terms it will be 0. So that means this double summation will now become a single summation, and wherever m is there we have to put n. That means I will have modulus Cn square into En. So this is your Eg. Now notice,
Sir?
yes.
Sir, here H in that phi n basis, that is the matrix element, no? Emn. Why are you assuming it is diagonal in that?
No, I am, so by definition, I started with this basis. No, this is an eigenbasis of Hamiltonian. So
Yes,
H is
sir.
diagonal in this basis.
Oh, okay, sir.
So I have chosen the basis as the eigenbasis of H.
Okay, okay. Thank you, sir.
So now note that En is greater than or equal to E0 for all n. Agreed? We don't know En. Okay, so we do not know them. But this statement we can make. Even if we don't know, whatever is the energy level, it will be larger than the ground state energy level, because ground state energy is the smallest energy. Correct? So now what I say, instead of every possible energy, if I put ground state energy, okay, if I put ground state energy, what can I say? Since En is greater than E0, suppose, so if we substitute for En, substitute E0 for all n. If you do, what will happen? Right hand side will be sum over n modulus of Cn square into E0, because every En is only E0. If I substitute, I can pull that out. So what is that equal to? Sum over n modulus Cn square is 1. So this is simply E0. Correct? So the right hand side becomes E0. But that is not equal to left hand side, because left hand side is with all Ens are there. But if I put En is equal to E0, in every term, we are actually getting some smaller value, because En is greater than E0. I am putting E0 means what? I will get a smaller number. Correct? So we can say that this Eg is a greater value than this one, which is equal to E0. So this is the proof that the expectation value, which I defined it as Eg, is greater than E0. Or in other words, this implies E0 is less than or equal to E. So this is the proof of this theorem, which simply tells you that you take any state you want, find the expectation value, that will always be larger than the ground state energy. Or in other words, that would give you an upper bound on the ground state energy. Now, there is an important remark I would like to make. The remark is the following. This has an advantage. Suppose I tell you, okay, you give me I give you Hamiltonian. Okay, so let's say given the Hamiltonian, let's say two of you will choose two different functions. Okay, so let us say that one chooses psi and another chooses, because this is something which I tilde. Now we can say that which one is the better choice. Okay, which one is the better choice? So that we can decide. Okay, so we can determine the better choice. Which one is the better? Because now what you do, you try to get the expectation value of the Hamiltonian with this one, and you try to get expectation value of Hamiltonian with this wave function. Call that as Eg and Eg. Okay. Now if you find Ej tilde is smaller than Eg, this implies psi tilde is a better choice. Okay, if you choose psi, then Eg is the upper bound. Now you are getting something smaller than that. That means it is more tighter upper bound. So that means psi tilde is a better choice. Okay, so this will tell us that if you can choose, okay, so you call this the choice of psi, okay, is sometimes called Hess wave function, Hess wave function, or sometimes we call as a trial wave function. trial wave function. Now what you can do is that you allow certain set of parameters. This lambda can be one parameter or can be a set of parameters. Okay, so these are parameters. So you choose the state with some floating parameters. You do not know these parameters, but you can choose these parameters. Now, if you try to find out the expectation value, what happens is that this EG itself will be a function of parameters. EG, which is the expectation value of this psi of lambda h psi of lambda. So this EG will be itself a parameter. Now, if you change this parameter, if you are changing this parameter, then if the changes in a direction such that EG is decreasing, then that changes, you are going to better and better, better trial wave function. So what one does is that to get a better choice, okay, so to get a better estimate of so better, I mean what? Better means closer estimate of E0. So find lambda that minimizes EG of lambda. Okay, so let us say find lambda that minimizes EG of lambda. So let us call it some lambda star. Okay, so now you can say that EG, you substitute that lambda star is the best estimate of EG. So it's still not equal to E0, but you can say that it is the best estimate of EG. Okay, so this is what you will do to find out the ground state. Now let's try to look at some examples and then see how we can. So let's say,
Sir?
Yeah.
Sir, here, sir, how to choose this psi? Can we start take psi as the eigenfunction of unperturbed Hamiltonian and then develop? Will it work, sir? Means a psi as eigenstate of H0.
Yeah. So, but right now what I'm trying to say is that you don't have H0 and H prime here. We are not able to divide it like that. But if you, for example, in many electron systems, it is that kind of a independent electron state. That is what is taken as psi0 sometimes. I mean, guess wave function sometimes. Okay, so it works. It works in some cases, but your trial wave function you must construct with certain parameters. Okay, so there is some.
Is there any procedure to make a guess for this trial wave function?
So try see, whenever you are saying it is a guess, okay, so there is a fair amount of intuition that is involved. Okay, if I can give a method, then I will not call it a guess. Right? So whenever we are saying we are guessing something, that means there's fair amount of intuition that is required, that is involved, and this intuition is something that we have to only gain by looking at how people have done it, and so we'll have to just look at how people see. When people did it, they had some logic, of course, but then most of the times it is out of some out of hat idea that would have given them a better guess.
Yes, sir. Once, sir, I asked you how to get a intuition. You told me it will not come by tuition.
Yes, intuition will not come by tuition. That's what I believe. So if that comes by tuition, then I think there will be a lot of tutorial colleges again for that one.
Yes, yes, sir.
Yeah.
So for many electron systems, how this variational method is useful, sir? So I thought that in many electron systems, we have the spinning constant. Like electron spins the nucleus. So we instead of Z, we have Z effective, which is Z minus sigma. So that's how we deal with the many electron system. But how we many electron system we deal with the variational principle, sir?
Yeah. So there you are going to take your trial wave function as if these electrons are not interacting with each other, but there you are going to fix the parameter as Z effective instead of Z, and then find out what is this effective Z by minimizing the ground state energy or the expectation value of the Hamiltonian.
Okay, sir.
So I think first what we can do is we can try to do a simple problem. So the simple problem is something for which we know exact ground state. Okay, so let's look at harmonic oscillator. Okay, so one-dimensional harmonic oscillator. So you can say that you know the ground state energy E0 is equal to h cross omega 2. And what is the Hamiltonian? Hamiltonian is E square over 2m plus half m omega square. So this is our Hamiltonian. Now let's say we don't know the, so this is known for us, but let us pretend that we don't know. Okay. Let's assume that we don't know this ground state and we would like to find out ground state. Now I'm going to make a guess of my wave function. So I will say that psi of x is equal to some a into e to the power minus b x square. Like this, I will make a guess. Now, how do I make a guess? This is where some intuition will help. Like for example, we know that if you have a potential which is like this, so let's say this is v of x versus x. Okay. Now, classically, if you see that suppose if you have some kind of a marble, this marble is going to okay. Let us put it this way: it would like to spend more time. It will be stable at x equal to 0, and if you are displacing it, if you are increasing the energy, then it will try to come back to that point, right? So normally one can say that there is some kind of a correspondence between this potential and wave function or the probability. Okay, wherever minimum of the potential is there, there will be a maximum for the probability. Probability and also wave function as far as ground state is concerned, because ground state there will not be any node, wave function will not cross the x-axis. Because of that, the maxima of the probability will be coinciding with the maxima of the wave function. So because of this intuitive understanding, I know that probably Gaussian is this kind of a function is a better choice for this one. Of course, you may say that since you know you are choosing it, but that is why I am giving this explanation, that what goes in our mind when we are trying to choose a wave function. Now what we should do is we should find out this A. Okay, so that is what by doing normalization. So it is minus infinity to infinity mod A square into e to the minus twice b x square dx. Okay, so this is you know this, so this is equal to 1. Okay, so let us define root 2b into x to be some y. Okay, so dx is equal to dy by root 2b. So I have mod a square by root 2b into integral minus infinity to infinity e to the minus y square dy is equal to 1, and this is actually root pi. So this gives you that your A is equal to pi 2b by pi to the power 1 by 4. So I have determined what is my A. So now what I have to do, I have to find out. So first step is normalization. Normalize psi of x. That is our first step. Now second step is find EG, which is equal to expectation value of psi h psi. Okay, so this we can do it in 2 steps. First, we will find out expectation value of the kinetic energy. That is equal to so expectation value of kinetic energy is integral minus infinity to infinity and root 2b by pi is 1 by 4, so there will be 2 terms like that. Okay, so let me write like this first. That is integral minus infinity to infinity psi star of x. Anyway, this is a real function, so let me write it like this. And then, of course, I have minus h bar square into dou square psi by dou x square. Okay, now you know this psi of x. Okay, so this is a very general statement. So notice that whatever is your psi of x should go to 0 as x goes to plus minus infinity. This is a boundary condition. Okay, so this is a boundary condition, and every wave function should satisfy this boundary condition. Now, if you do an integration by parts of this, then what happens? You have minus h bar square, and let's say that so dou psi by dou x. Okay, dou psi by dou x. I can transfer 1 dou by dou x to this. Correct? Since psi goes to 0 as infinity, that boundary term will vanish. So I will have integral 0 to infinity. I have psi prime of x. If this is star, then it will be psi prime of x dx. So in general, you can say that the average kinetic energy is always modulus square of the derivative of the wave function. Okay, so you know this psi prime. psi of x is equal to a into e to the minus bx square, and psi prime of x, you can write it as a into e to the minus bx square into minus 2b times x. Okay, so this is minus 2bx. So let me put a here into e to the minus bx. So what will be square of that one? Square of that one will be uh, so h bar square into a square into 4b square to integral minus infinity to infinity. We'll have x square into e to the minus 2bx. Okay, so now you can do the same substitution, and so you get x is equal to y by root 2b. So then you have is equal to h bar square a square by 4b square divided by 2b to the power 3 by 2, because 1 2b comes from here and root 2b comes from here, and integral minus infinity to infinity y square e to the minus y square dx. Now this I can write it as 2 times 0 to infinity, and this is basically gamma of 3, gamma of 2p minus 1 is equal to, so which implies 3 by 2. Okay, so gamma of 3 by 2 is half gamma half r, that is equal to root pi by 2. So you can see that this can be written as h bar square. A square we know, a square is 2b by I, root 2b by pi, and then I have this one is 2b the square and divided by 2b into root 2b, that is this much, and you have a 2 and a root pi by 2. So this 2 will cancel, this root pi will cancel, this root 2b, this root 2b will cancel, you will have 1 2b here. So in effect, what I have is 2b h bar. Okay. So this is our average kinetic energy. Now the potential energy is B is that, let's calculate average potential energy. That is equal to integral minus infinity to infinity a square into okay, a square by 2 m omega square into x square into e to the minus 2b dx. So this is same as this one. Okay, x square into the minus x square. So that is
Sir, in kinetic energy term, M will be there, no? Kinetic energy term, M will be there, mass.
correct. So there is h square by 2m, right?
Yes, sir.
Is add that one. So that is dh square by m. Okay, that will be there. So now what we will have is this one, but this one is exactly same as this. So we will have so this is equal to a square m omega square by 2 into 1 by 2b root 2b into 2 into root 5. Right? So that is what this is. So this will cancel, and this a square is root 2b by pi into m omega square by 2 into 1 by 2b root 2b root 5. This will cancel, and root 2b will cancel, and I will have m omega square divided by 4. So you can see that the Eg is equal to, you have uh, b h bar square divided by m plus m omega square divided by 4. Okay. Now you can ask. So here this b is the variational parameter. If I change b, then it will be a different energy. Okay, so variational parameter. Now we ask a question: what b will give minimum value of Eg? So that we can understand if you take dEg by dB is equal to 0, that implies h bar square by m minus m omega square by 4b square is equal to 0. So that tells you that m omega square by 4b square is equal to h bar square by m, or in other words, you can say that you can take b square that side. So b square is equal to m omega square divided by 4 m square omega square divided by 4 h bar. So in other words, we can say this implies b is equal to m omega by 2h. So if b is equal to m omega by 2h bar, for that value of b, this energy will be minimum. Now you go back and substitute that. So Eg is equal to, so let's say m omega by 2h bar into h bar square by m plus m omega by 4 into 2h bar divided by m omega. Okay, so now you can see that h bar will cancel, m will cancel. So you have h bar omega by 2 plus, here you have 4b.
There is extra 2 factors are coming. Extra 2 is supposed to be h cross omega by 2, no sir?
H cross omega by, so I think h bar by omega. I don't know, let's just check this calculation. Phi prime is equal to minus 2b into x, that's fine. X 4b square, right? This is 2 times this, x square. 2 minus 1 is equal to 2, b by 2. Gamma half is root 5, 9.
Sir, in kinetic energy term, I think.
Hmm?
In kinetic energy term, I think that is root 2 times
Where?
in kinetic energy terms, sir. I am getting
Root 2 So this is m omega square by 4v. So m cancels, 1 omega cancels, 2. So I have h cross omega by 2. So I think overall we are missing some factor 2 in both cases. So y square. Oh, I think yeah. So I think what 2 times. Okay, that is correct. See, I think I made a mistake. 2 times integral 0 to infinity y to the power 2p minus 1 e to the minus y square dy is equal to gamma of p. This is the definition of gamma function. Okay, so I have written this 2. So then this 2, including this 2, it is gamma of 3 by 2. So I should not put 2 here. You follow, no? So gamma of 3
yes,
by
sir,
2,
yes,
which is
sir.
root 2 by 2. So that means I will have a 2 here, and then I will have a 2 here. That is 8. That will be a 2 here. So this 2 will be there, and this 2 will be there. Okay, so now we will have 2. That 2 anyway will not disturb us. This is correct. Now if we come back here, this will be uh, yeah. So there will be a 2 here, and this will be 8. So you get 4 and 4. So this will be h cross omega by 2. So what we have seen is that in this particular case, we are so lucky that we have got exact ground state value. That means our guess is so correct, so nice, that we have got exact ground state value. And of course, we know that the ground state value is same. And the wave function is also same because we know that, and hence there is nothing surprise that we have this ground state value to be this one. Now we can try to look at another problem. Let's say next example. Let's call this example 2. Example 2. So here what we can do is that let us take the Hamiltonian to be p square by 2m minus minus alpha times a Dirac delta function. I think we have done this problem earlier, and I am sure you remember what there is only one bound state for this, correct? And I think
minus m alpha square by 2 h cross 2 power 4.
minus m alpha squared by
2 h cross 2 power 4.
huh?
H cross 2 power 4, I think.
To the power 4.
Square.
No, I think it is just h square.
Square, okay.
Okay. So this is the bound state of this one. I mean the ground state. This is exact ground state. This we know. Okay. Let us again pretend that we don't know this, and then uh, you also know that this particular potential has got a delta function like. Okay. Now you can see that this is very deep peak here, but let's assume that we may have a wave function to be something like this. Okay. So let us use the same wave function. So let's say my trial wave function is psi of x is equal to a into e to the minus bx. Okay. So that we can use some of the calculations that we have done. So your a is going to be same, right? 2 times b divided by pi to the power 1 by 4. Okay. So this is by normalization. Now your kinetic energy is going to be the same. So what will be the kinetic energy? I have chosen the same thing because I can use some of these results. So kinetic energy is Bh bar square by 2m. Kinetic energy is Bh bar square by 2m. We have to calculate the potential energy. The potential energy is going to be a square integral minus infinity to infinity. You have a minus alpha into delta of x into e to the minus 2vx square dx. Now what is this? A delta function integration is very simple. Wherever x is there equal to 0, then this simply becomes 1. As e to the 0 is 1. So that is equal to minus alpha into root 2b divided by. So what will be your Eg? Eg is equal to, you have this kinetic energy, where is kinetic? Bh bar square by 2m, Bh bar square by 2m minus alpha, okay, root 2 by pi, and then you have root b. Okay, so now we have to choose a b that will be that will minimize this Eg. So now you ask what is Eg by Eb is equal to 0. That implies h bar square by 2m minus alpha root 2 pi into 1 by 2 root b is equal to 0. Okay, or in other words, we can say, okay, this is equal to 0. So now you can say that h bar square by 2m is equal to alpha 2 by root pi into 1 by 2 root. So this 2 and this 2 will cancel. So take b on this side. So root b is equal to alpha root 2 by pi into m by h bar. Okay. So now take square both sides. B is equal to alpha square 2 by pi into m by h bar square. Okay, so our b is equal to twice m alpha square divided by pi h bar. So this is the value of b which minimizes its Eg. Now go and substitute that one here and find out what is your Eg. So Eg is equal to twice m alpha square divided by pi h bar square into h bar square by 2m minus alpha into root 2 by alpha into what is
Sir, you need to square that m over a square term.
where m over
H could square. That you also take the square, right?
2 by 5 okay, right, m square h bar to the power 4. Yeah, so that means m square h bar to the power 4. Yeah, and root b is you have alpha root 2 by pi 2 by pi into m by h bar square. Okay, so now you see that this is equal to this 2 will cancel and h bar square will cancel with this h bar square and one m will cancel this m. So that is equal to m alpha square divided by pi h bar square minus. So I have alpha square and 2 by pi into m by h bar square. Okay, so you can see that this is m alpha 2m alpha square by pi h bar square, and this will be minus m alpha square divided by pi h bar square. So this is your Eg. Now compare this Eg with compare this with your E0. What was E0? E0 is minus m alpha square divided by 2h bar square. Now pi is greater than 2. Okay, pi is greater than 2. So this will be a smaller negative number. That means this energy is larger. Okay, so Eg is greater than E0 since pi is greater than. So whatever trial function that we have taken with this choice of B, this is the best estimate that we can get. But this is not equal to this Eg, but this is something which is different from Eg, but it is a larger value. Okay. Now I will leave this for you to do this exercise. Okay, so choose another trial wave function. Choose another trial wave function for the same problem, for this Dirac delta problem. Yeah.
If we take e to the power minus mod x, then
yeah, correct. So I am now saying, okay, you choose your psi tilde of x as some a into e to the power minus b mod x. Okay. If you choose this wave function, you please repeat this calculation. Then you will see that for some value of b, okay, and it turns out b is equal to alpha, for some value of b, you will get exact ground state energy. Okay, because this is the right wave function for this problem. So if you choose a trial wave function of this type, then it will definitely give you exact ground state value. Okay, so this is something which is the procedure. Yeah.
Sir, sir, here number of parameters to minimize the ground state, we have chosen only one, sir. Is that related to dimensionality of the problem, or that is independent?
No, it's not related to dimensionality of the problem. See, these are just illustrations. Now, your trial wave function can have any number of parameters, and usually, if the number of parameters are increasing, then it is like you can search in multi-variables the minimum function, right? So it is generally believed that if you can have more number of parameters, then you can get better and better estimate of the ground state energy. But then you cannot also simply put so many parameters, because that parameters should make sense, right? So if you have a Gaussian function, I can have there's only one variable, so I can have only one parameter defining it, right? So, okay, in some sense, you can say that if you have a wave function of one variable, then you can have only one parameter, because if you take two parameters also, they can be redefined as one parameter.
Because they are not independent in that case.
Correct.
Okay.
Okay. So this is an example, but let me just try to give one. So you know this when we have this helium atom, for example. Okay, so I don't know in the list that you people have given me, I think hydrogen atom is there. So I don't know if I can talk about helium atom without hydrogen atom. But let me assume that you know some hydrogen atom. So let's look at what happens to helium atom. So helium atom is has nuclear charge is nuclear charge is 2 times E. There are 2 protons, and neutrons have no charge, and there are 2 electrons. So the Hamiltonian, assuming that this nucleus will not move, nuclear motion is slow, can eliminate the degrees of freedom. So let's assume we are only talking about 2 electrons. So P1 square by 2m. Both are electrons. So let me not differentiate. So P2 square by 2m plus the electron will have so 4 pi epsilon naught R1 minus 2e square by 4 pi epsilon naught R2. This is first electron interacting with the nucleus, second electron interacting with the nucleus, and then of course there is an electron-electron interaction. So that is given by the modulus of R1. So this is the total Hamiltonian of this helium atom. Now you can,
Sir?
yeah.
So we have made an assumption that electrons can be distinguished. You know, the P1 square is the kinetic energy of the first electron, and P1 square by 2m, the kinetic energy from the first electron, P2 square by 2m, the kinetic energy from the second electron. So they can be distinguished here.
See, at the level of Hamiltonian, we have to say that there are 2 electrons, and this indistinguishability or identical nature of the particle is always a kinematic effect, in the sense that only when we try to write down the states that that symmetry or antisymmetry of these particles will have to be considered. At this level, I will not be able to consider them to be indistinguishable, because there are 2 electrons. Which is what electron is a different thing, but there are 2 physical electrons, right? So I have to write down 2 kinetic energy terms. Yeah. So now, suppose let's say that let's assume that this guy is not there. Okay, so this term is what we call as potential of electron-electron interaction. Okay, so assume VEE is equal to 0. That means there is no electron-electron interaction. In which case, if you want to find out the ground state of this one, that is very easy, because you know the ground state of hydrogen atom. Okay, so a ground state of hydrogen atom is minus 13.6 electron volt. This corresponds to Z is equal to 1. Okay, now if you consider hydrogen-like atoms, okay, so hydrogen-like atoms, then your E0 is equal to minus 13.6 into Z square electron volt. That will be the change, because energy is Z equal to 1 is minus 13.6 electron. So for an electron in helium atom, this is for hydrogen, this is for hydrogen atom, this is for hydrogen-like atom with the nuclear charge Z times C. The nuclear charge Z times C. Now helium atom. So for helium atom, Z is equal to 2. So one electron will have an energy of minus 13.6 into 4, but we have 2 electrons. So ground state energy for helium atom, ground state energy can be written as, or this is what I am estimating. So ground state energy can be written as minus 13.6 into 4, but then there are 2 such electrons, so it is 8. So which is equal to okay. So this is equal to
108.8, sir.
108.8. 108.8 electron with a negative sign. So this is what I would have estimated as ground state energy if I assume that the electron-electron interaction is negligible. Okay, but from ionization experiments, the experimental ground state is well known, that is equal to minus 74.778, something like that. So this is the experimental value, and this is quite different from this. Correct? So what this tells us that so we cannot neglect VE. This is the lesson. Okay, so this is the lesson from this. Otherwise, this is too much off. Now, what you can do is you can say that if you have so if your VEE is equal to 0, okay, then you can have your psi of R1 comma R2, psi of R1 comma R2. This is a 2-particle wave function, can be written as some constant into e to the minus 2 R1 plus R2 divided by 2. So this is basically the hydrogen atom state. Okay, basically psi of R1 and psi of R2. So this is the wave function.
Sir, can I divide in scatter determinants?
Huh?
In scatter determinants?
No, this is just a product state. Okay, this is just
2
a
electrons are there, 2 fermions.
Yeah. So basically, right now we are just looking at the ground state. Okay, so this ground state is simply the state of R1 and state of R2. Okay. So this is ground state of first electron. This is the ground state of the second electron. Okay, so I'm not taking Slater determinant. It's just a product. Now, if you take this product and then you go and then try to ask what is the thing, when you do this, okay, when you try, let's say this is my trial wave function. Let's say this is my trial wave function. Then what happens? Your expectation value of the Hamiltonian will be so first up to this term, except this VEE term, up to this term, that is going to be minus 108.8 electron volt, plus you have to take an expectation value of EE, so that is your VE expectation. Okay, so you have to calculate the expectation value of this VEE. Okay, and if you can calculate that and then add it to that, then you will get a value which is different from this minus 108. Okay, so I will not do this calculation, but I will just tell you, because this calculation is something which is not difficult, but some amount of bookkeeping is required. So you can see that so there is something called A here. I have to of course determine this A, but you can take this A from the constant normalization constant of this hydrogen atom. So let's say that I have calculation of this VEE, that is A square into integral e to the minus, let's say 4 times R1 plus R2 divided by A, because I have psi star and psi, into you have E square by 4 pi epsilon naught into R1 minus R into, of course, D3 R1, D3. Now, doing this integration is a little bit involved, in the sense that without any loss of generality, without any loss of generality, you may assume that you have a coordinate system where your R1 vector is along this Z axis and R2 is in some direction. So this theta 2 becomes an azimuthal angle. Okay, if you identify your R1 as so choose R1 along Z axis. Okay, now if you choose this, then you can write down this 1 by R1 minus R2 modulus as 1 by square root of R1 square plus R2 square minus 2 R1 R2 cos theta. And you write your D3 R2 as R2 square sin theta 2 d theta 2 and d phi. And then you can integrate this. First you integrate over D3 R2. Okay, so that means you will have this VEE expectation value will be A square integral d3 r1 e to the minus 4 r1. This part, let us keep it like this. Into you have an integral which will be I2 as a function of R1. Now, what is this I2 of R1? I2 of R1 is equal to integral the integral R2 square dr2 sine theta 2 d theta 2 d phi 2 into e to the minus 4r2 divided by a, 4r2 divided by a, divided by square root of r1 square plus r2 square minus 2r1 r2 cos theta. Okay, so d phi 2 integral, there is no phi 2 dependence, so this will become a 2 pi. Now sine theta 2 d theta 2, there is a theta 2 here, so you take cos theta 2 is equal to x, and then the sine theta 2 d theta 2 will become dx or minus dx. From 0 to pi will become minus 1 to plus 1, and then do this integration, and then after that perform the integration over dr. Then you get this integral over this one. Then you do an integration correspond to in just 1 minute I have okay, so I think I will not be able to continue because as I told you that my plug point has given some spark. So I was I was running with my laptop battery so far. Now this battery has come to less than 10%, so it might stop. So what I can say is that these integrals you can continue doing it, and maybe you can look at any book like Griffiths or any book on quantum mechanics. This Griffiths or Coherent Energies volume 2 or volume 1, one of those things. So this integration you can try. Then you will see that this VEE average turns out to be something like 34 electron volts. So minus 108 plus 34 will become minus 75 or something like that. But that is also not a satisfactory thing. So what one does is when you take this instead of this 2, you will always choose something called some Z, Z or Z prime, so that you will get ground state energy as a function of Z prime. Now minimize Z prime, minimize ground state for some Z prime, and then you will see that this Z prime will be a number that is something like 27 by 16 or something like that you will get, which is roughly 1.69 something like that. That means it is less than 2. So this is what is called screening. That means the electron-electron interaction will essentially screen the nucleus. That means each electron will not see the nucleus as if it has got charge 2e, but it will only see as if it has got a charge of 1.69e. So because of this idea called screening, one can use this Z prime as a parameter. And if you incorporate this one and find out ground state energy corresponding to this Z prime is equal to 1.69, you will get almost very accurate result for the ground state of the helium atom. Okay, so I will stop here because this laptop will get switched on off anytime, and so we will continue with another topic in the next class.
Thank you, sir.
Hello, sir.
Yeah.
Sir, can you please share the notes of last class and today's class?
Okay. I think I forgot last time.
Okay, thank you, sir. Good night, sir.
Thank you, sir. Good night, sir.